When it comes to probability, there are basic properties of probability, sometimes called general rules, that are important for a person to know. So we have the following example to work with, and you should have this example also available for you that you need to fill out online as well. A standard literacy test consists of 100 multiple choice questions, each with 5 possible answers. There's no penalty for guessing. A score of 60 is considered passing, and a score of 80 is considered superior. When the answer is completely unknown, test takers employ one of 3 strategies: guess, choose C, or choose the longest answer. The table to the right summarizes the results of 1,000 test takers. So, first thing is first is whenever you have what is called a frequency table, you should utilize that in order to answer any question that contains the probability. So this frequency table can answer all of these questions without you really needing to know any of the probability rules. Because what you use is utilize everything that's inside the table in order to strategically figure out what the answers would be. For example, we can answer the first 4 questions together. What is the probability that someone in this group uses the guess strategy? So first we need to know the total number of people in the entire study, which is 1,000. Then we need to figure out who are the people who guess, which is located right there. So we can say that 300 out of 1,000 people guessed on this test, meaning the probability of choosing a person who does that is 30%. Furthermore, we can continue with 60 to 79, which is 530 over 1,000, or 53%. Then finally, what's the probability that someone scores 0 to 59, or scores 60 to 79, or score 80 to 100? What we would do is add up all of the people who are featured in that, which just so happens to be the entire sample size. So the answer is 1,000 people out of 1,000 people, or 100%. And the same for question 4. The probability that someone guesses, chooses answer C, or chooses longest answer is everything that needs to be added up vertically, which is, again, 1,000 divided by 1,000, or 100%. So these first 4 things actually talk about the first 2 rules of probability, which are for any event in probability, any event E, the probable outcomes have to be between 0 and 1 inclusive. Probability can't be any more than 0 or any less than 1. So when someone tells you that something can go 110%, they are absolutely lying to you. That is not a true statement, and that can never really be seen as a possibility. The second thing is the sample space. A sample space has to add up to 100%. So if you know all of the possible outcomes, then you know 100% of what's happening in that event. Continuing with this example, we can go to a few more questions here. What is the probability that someone guesses or chooses answer C? So first we want to see all the people who guess, which is 300, plus all the people who chose answer C, which is 320. So 300 plus 320. Okay? Now, the one important thing we need to ask ourselves is, are these 2 events mutually exclusive? The answer to that is yes. You can't guess and technically choose answer C as your guessing strategy. You can guess answer C, but you can't choose answer C by guessing. So the probability of that is adding up those 2 things together, and we get 620 out of 1,000. 620 out of 1,000, or 62%. Question 6 here says, what is the probability that someone chooses longest answer or score an 80? So we need to see all the people who chose the longest answer as their guessing strategy, which is 380, and then all the people who scored between an 80 and 100, plus 350. Now, again, we have to ask ourselves, are these 2 events mutually exclusive? In this case, the answer is no. Someone can choose the longest answer as their guessing strategy and score an 80 out of 100. Those 2 things can happen at the same time. If that's the case, we must deduct the intersection, because notice that when we first looked for the longest answer, we added 135 here. Now, when we want to see all the people who scored 80 to 100, that also includes 135. So we have to avoid double counting there. So the probability, just do some mental math here, 730, 135, 595. So the probability there is 59.5%. What's the probability that someone scores 60 to 79? So we went over that a little bit earlier here, and the answer was 53%. So what if we want to know the people who did not score between a 60 to 79? While we could add up 120 plus 350 to get the answer, remember, the sample space has to add up to 100%. So if we're interested in an event not happening, what we can do is subtract 100%, 53% from 100% to get that probable outcome of getting between a 60 and a 79. These are also probability rules. The first is the complement rule. For any event E, the probability of E happening plus the probability of E not happening, the complement, has to equal to 1. So that means that if you know an event, the probability of that event not happening is equal to 1. This is a really, really, really useful rule. And we're going to see more of that in class as to why. Then the fourth and final property here is the addition one. If two events E and F are mutually exclusive, then the probability that they happen is E plus F. If two events E and F are not mutually exclusive, then the probability is E plus F minus the intersection, because we want to avoid double counting. One useful tip is that this rule can actually apply to this rule, because if the events are mutually exclusive, then the probability of E and F simply equals 0. I added a couple more questions here just to round out this unit. Question 9. If a person is considered superior, then what is the probability that person guessed an unknown answer? So now we're not choosing out of the entire total. Instead, we're only choosing the superior students. And the superior students were anyone who scored above an 80, so 80 to 100. So our sample space is now actually 350. And then out of the 350, who guessed an unknown answer? So who used the guessing strategy? So we only look in the column for those who score between the 80 and 100, and we notice that 100 of those people guessed, and that's how we're able to figure out our conditional probability. This is called a conditional probability. Question 10 here is a person guessing an answer independent to a person being superior? We're going to work more independence and together in class, but I'm going to show you the definitions of those. So the formal textbook definition of a conditional probability is a probability that takes into account a given condition has occurred. The conditional probability formula, first and foremost, the symbol for a conditional probability is a bar. Kind of looks like an absolute value bar, but it's a bar in between two events. So this is saying, what is the probability of B given that A has happened? The answer to that is, it's the probability of A and B happening at the same time divided by the probability of A happening. So notice in our previous example here that in order for us to get this conditional probability, first event A, superior, had to happen. So that does happen. 350 people were superior. Out of those, how many guessed? In order for us to know that, they have to remain superior and they have to employ the guessing strategy, which is this overlap here of 100. The last thing we want to talk about is independent events. Two events are independent if knowing that one will occur or has occurred does not change the probability, that the other occurs. So two events E and F are said to be independent if the probability of E given F is equal to the probability of E. Or if E given F is equal to E, it is also true that F given E is equal to F. So what this is saying is that, say you put a condition in, it does not change the outcome of another event. That does not mean mutually exclusive. That just means that the probable outcomes do not change. So in order to answer this question, first we need to figure out one of the following situations. So let's first just focus on a person being superior. A person being superior has a probable outcome of 350 over 1,000. Now we want to see what's the probability of them guessing given that they are superior. So remember, that was 100 over 350. If these two things equaled each other, then these two events would be independent of each other. But because they are not equal to each other, they are actually dependent of each other. So those are the general probability rules. One last thing that I want you to take into consideration, in general, if any two events have an intersection, then the numerical way to find them is first figuring out the probability of one event, say the first one A, and you multiply that the probability of B, given that A has already happened.